copper is located here. You can see 29 electrons in the middle of the periodic table. So there's where we can go to look for it. And I do not expect you to memorize the periodic table or know where all these elements are, but do know that, you know, what the number means, number of electrons, and maybe, you know, a few of what some of them are. Now on your lecture quiz, yeah, I'm going to ask you what some of the atomic symbols are, but on your main quiz, I'm not going to ask you to know all those. That's for chemistry class. Alright, but here's what's really happening, alright? What's happening with those electrons? So it kind of brings up, you know, magnetics and things like that. So remember, opposites attract, likes repel. Alright, so this is how electronic forces work, or current works, because they're not what's on the right hand side. That's not current. Current's actually on the left hand side. That's how we make it flow. Alright, we have like charges. Those like charges push on each other, and that's how we make it flow. If we had opposite charges, they would attract to one another, and that's what we don't want. So when we give a force, which is voltage, and we apply it to current, all right, or we make current flow, okay, we have like charges that we're pushing around here. So don't necessarily pay attention to the positive and negative. In copper, we're pushing the electron, which is symbolized with the negative. So imagine like two negatives hitting each other. We're pushing them so that they go back and forth and create friction and the flow of electrons. Okay, so for us, how do we calculate what that charge is? Well, the unit of charge for us, we first got to understand, is what we call a coulomb. Okay, and we covered that in some of our SI stuff earlier. We're going to just remember this piece. This is the only chapter we're really going to focus on charge and things like that until we get to capacitors and charging things up. So 1 coulomb is the total charge possessed by 6.25 times 10 to the 18th electrons. That's a lot of electrons, right? That's 6.25 times 10 to the 18th. We learned about that when we were doing engineering and scientific notation. That's a really large number, so that's why we can write it, you know, in either engineering or scientific notation. That number's written in both. So how do we calculate total charge? The variable we use for charge is Q. So we will be solving for Q. So to find the total electrical charge that we can get out of something, we're going to take the number of electrons that it possesses divided by 6.25 times 10 to the 18th electrons per coulomb. Alright, so charge will be in coulombs. Alright, so let's take a look at an example here. We have how many coulombs of charge do 88.7 times 10 to the 15 electrons represent? Alright, so what we're going to do, we're going to take that 88.7 times 10 to the 15th, divide it by 6.25 times 10 to the 18th, alright, and that's going to give us the actual charge. Now when you're using your calculator, alright, make sure that you pause the video and make sure you get the right number that I'm getting. Put the numerator in parentheses in your calculator and put the denominator in parentheses when you do this. That way there won't be any issues or you forget one or the other. Put the entire numerator in parentheses, so 88.7 times 10 to the 15th, close parentheses, and then put the 6.25 times 10 to the 18th in its own set of parentheses. Then hit enter when you do this division. Alright, so when you get that, and you know, this applies to the properties of exponents that we did before. You can really just take 88.7 divided by 6.25. That's where you get 14.91. And then remember the base is 10. When we divide and they have the same base, we subtract the exponent. So that's why it's 15 minus 18, which gives us -3. Your calculator will do that for you as well. You can put your calculator in scientific or engineering mode, and it will do that. You just need to remember that you do that, because later on you're going to use it in a different class and be like, why am I getting these weird numbers? When they mean the same thing, they're just going to be in different notation. So for us, it's 14.91 times 10 to the minus 3 coulombs, or we say 0.01491 coulombs. So either way, could we say what's the SI on that? Yes, it would be 14.91. 10 to the minus 3 is what? Milli. So we would say 14.91 millicoulombs. So that would be the correct, most accurate way that we would say that number. Alright, so let's talk about voltage now. Voltage, that's the force required to move a charge, what we just calculated, against the electric field. So what's the whole point of this? We are moving charges so that we can make electron flow. Okay? Work equals force times distance. So when we apply force over a distance here, we get work done. Okay? You learn a lot more about that in physics and things like that. But, alright, we're taking voltage, by definition, is the work per charge done against the electric field. We've got to overcome that field and start forcing electrons to flow. Alright, so that's what voltage is doing. We're taking those electrons and we are pushing them against the other electrons, right? Because we want to get them to flow, because remember, why are we doing it this way? Because opposites attract, likes repel. We want to take likes and push them so that they repel and so that they flow. Alright, the equation for voltage, we're really only going to use this in this chapter as well. Okay, voltage is energy divided by charge. Please be careful that that's not watts. That's energy, joules of energy. So when we refer to energy, we talk about joules. Alright, so it's energy divided by charge. So W over Q. This is the basic calculation for voltage. This is the fundamental calculation for voltage. This isn't really going to how we're using it all semester. There's a different relationship we're going to use in Ohm's law that kind of changes up how we apply that. Alright, so definition kind of down here. 1 volt is the potential difference between 2 points when 1 joule of energy is used to move 1 coulomb of charge from one point to another. So moving joules of energy, alright, divided by charge. That's how we're going to get that voltage. Alright, so let's do an example here. I have 135J, that's for joules of energy, are required to move 15 coulombs of charge. What's the voltage? Alright, so in your head, you should have written down the voltage equation, so make sure that when you're taking notes through these, alright, that you are writing down the equations. Always pause the video, make sure you have a chance to write it down. That's much more advantageous for you guys to have the video, because you can pause it, you can go get a snack, take a break, come back, take notes, alright, not lose focus, not fall asleep, because I know this is super exciting stuff, but make sure that you're taking notes that you can reference to, because, you know, on a test or something like that, you're not going to have access to the video or things like that. So you got to be able to study, alright, and it's better if you have notes neatly organized. We'll talk about that in person a little bit in class too. Alright, back to the problem here. 135 joules of energy required to move 15 coulombs of charge. What's the voltage? Voltage is energy divided by charge. So you're going to take that equation, substitute in the values we have. So we're going to have 135 divided by 15, and we're going to get 9 volts. Essentially, that's your 9 volt battery, in essence, if we had 15 coulombs of charge. Kind of just depends on, you know, the force we need. But just kind of an example there for you guys to go off of. So make sure that you write this down and know these symbols. The bars do mean something on this, so make sure you pause, draw this accurately. This is the symbol for a DC battery. Okay, AC is going to look a little bit differently. And it is important. There's 2 long bars and 2 short bars. When you draw this, the long bars are positive, the short bars are negative. So notice that we're completing a path here, positive, negative. We're going to talk about how current actually flows here in a little bit. But what's the purpose of voltage? That's the responsibility of voltage, is to establish the current. We're applying that force to make the electrons flow. 2 different ways we do it. We can use batteries in parallel. So that means each one of those is like a AA battery. Alright, if we connect 4 AA batteries in parallel, each one of those, alright, is 1.5 volts, and the drop across all of them at once is 1.5 volts. If we supply batteries in series, like your flashlight or something like that, alright, if they're wired in series, we can add up all the individual voltages. So if each one of those is 1.5 and there's 4 of them, 1.5 times 4 is 6. Alright, so that would be 6 volts. So there's the difference of how we can use batteries in parallel versus batteries in series. We can use series batteries to get more force, okay? But batteries in parallel, we're always going to have a nice constant voltage across them. Can you physically look all the time and see, hey, is this parallel or series? You need to track down kind of the connection pieces to see, you know, if what you plugged in, or battery-wise, if you put them in, are they in series or parallel? It just kind of depends on the operating voltage of what you need. Okay, so batteries. Okay, this is like one that's in your car. Here's the misconception about batteries, is that batteries really don't store a charge. Now, I know that that's kind of opposite of what you think, right? You're charging your phone. You're really not charging your battery. You're undoing and doing a chemical reaction. So when you require voltage, you're doing a chemical reaction. When you plug a battery back into the terminals, all right, to quote unquote charge it, you're undoing that chemical reaction. So saying the word charging your battery is technically incorrect. You're undoing the reaction. Charging has to do with capacitors. So batteries store the potential, all right? They have chemical energy in them, and they can produce that voltage force that we need, okay, to make current flow. And car batteries are the best ones you can look at, especially if you have a maintenance battery where you got to dump in a little bit of water, and you can actually see kind of the reaction taking place, because you can kind of see it through on some batteries. So we're just going to talk about some voltage sources right now. So batteries are one. Okay, so don't say that we're charging a battery or reversing the chemical reaction. That sounds so much cooler than saying I gotta go charge my phone, right? I'm gonna go reverse my chemical reaction. But fuel cells here. Okay, so a fuel cell is slightly different. We're converting chemical energy into a DC voltage, and we're gonna combine some sort of fuel. In this case, and the most common one is hydrogen and oxygen. So we can combine hydrogen and oxygen, in that reaction process, okay, creates electron flow. So another source when we use a fuel cell. You guys might have done this in the STEM class or something, and had a little car and dump some water in and watch it go. Another way, we talked a little bit about this when we were doing silicon, right? Solar cells. So we have the semiconductor layer on the top and the bottom, and that's our silicon, and we can either make it positive or negative and do that sort of thing. So this is how the basics of a solar cell kind of work. And that light reflects, all right, and through that semiconductor we can create and get our positive and negative terminals, and we can get a voltage. Now, solar is very, 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 very inefficient, all right? If you've ever seen solar, to get enough power or current off, so you don't have enough panels. I mean, if you actually go by a real solar plant, they have thousands of acres of panels, all right, and they're pointed at the sun. So in the morning, all the panels are facing east, and then by the afternoon, all the panels are facing west. They have to have it so it tracks the sun the entire day, so the panel actually rotates. But solar is very, very, very inefficient. And it takes, acres upon acres of these solar panels to be efficient and actually get enough current and voltage for you to supply. You can't go down to Radio Shack and buy one of those little solar panels and expect it to do, anything or any wonders for your house. I can't even charge your laptop battery, or sorry, I said charge, but undo the chemical reaction on your laptop battery, okay? So solar, very inefficient. Unless you live out west where they get like 350 days of sunlight and you got big panels. Alright, basic power supply for us that we're going to use. Ours don't quite look like this, but this is just a DC power supply. So we can plug it into the wall, alright, and then it converts it to DC for us, and we can vary, anywhere from 3 volts up to 12 volts of electricity for you there. So here's a little misconception. All right, electrons flow from negative to positive. All of our calculations we are going to do, and everything that you're taught in physics and that sort of thing, is conventional current flow. So in our mind, we think things flow from positive to negative. And for a couple hundred years, that's exactly how we did all the calculations in electrical. And we still do them that same way today. But when the electron microscope came out, we actually saw that electron flow is negative to positive. It's actually the opposite way. It does not change any of our calculations. Alright? But the conventional current method, the one you and I are going to talk with and how I'm going to use in class, is we are going to assume current flows from positive to negative. In real life, electrons flow from negative to positive. That's why when you're jumping your car battery, the very last cable that you connect is the negative cable. All right, if you already have that connected and you touch something else, that's where you can get hurt. Connect the negative last, because that's why electrons flow. So it sounds backwards, but it's because how electrons really flow versus conventional current flow method. So lastly, all right, we've calculated voltage and we've calculated charge. So now we're going to use charge to calculate current. So how much charge over a specified period of time, okay, to create how many electrons are flowing, or our current flow. So the definition of current for us is charge over time. How many electrons or coulombs of charge are flowing over a given period of time. So Q over T. Time is going to be in seconds. Okay, charge Q is in coulombs. I is amps. That's going to be our current. So 1 ampere is the number of electrons having the total charge of 1 coulomb moving through a cross-section area in 1 second. Think of if we cut a wire and we were just to try and be able to observe what's going on. So if we look at this one, all right, so let's say that this is our wire and we have a cross-sectional area. You can kind of see those little white dots flashing. Okay, that's really what's going on. Okay, those are our little coulombs of charge there. So just basic calculation, what's the current going to be if 2 coulombs of charge pass a point in 5 seconds? All right, so you can take a second to write this down, and then we'll do the calculation. Our Q is 2, our T is 5, and if you take 2 divided by 5, all right, you're going to get 0.4 amps. Or you could say 400 milliamps if you wanted to, but 0.4 amps is just fine. Another way, just remember, if I give you a problem that gives you work and voltage and you have to find charge first, I might give you a 2-step problem. I remember that charge is work over voltage as well. Current source. So this is a symbol that you need to write down. These are not as common, but we can interject a current into a circuit somewhere. I don't have one of these in my lab. I really don't know many people that do. Maybe it's your university level where you actually have to do a bunch of experiments and things like that. Even in industry, you know, it's not as common to interject a current source. But the symbol looks sort of like an AC voltage, all right? But it's a circle with a line through it. It's very imperative that you draw that arrow. I said line, but it's an arrow through it. The arrow represents current. If that was a circle without an arrow, it would be an AC source, and we put a tilde in it instead. All right, but know that this is a current source when you see that symbol. All right, we're going to talk a little bit about resistance and conductance. So remember, resistance is we're limiting the flow of electrons. So resistors limit the flow of electrons. They limit current. Conductance is the reciprocal of resistance. Conductance is how well something flows, or how well current can flow, or voltage. Okay, the notes here have voltage, but it's more current is flowing. Okay, so how do we calculate conductance? Conductance with a capital G is 1 over the resistance. All right, so this is how well something conducts, and the unit for conductance is a Siemens. All right, some of you guys are, oh, that makes sense now. I got to take the Siemens test shortly that you talked about in the next year or so. Okay, so Siemens is the unit of conductance. Resistance, all right, we do most things in terms of resistance. We don't do a lot of calculations in terms of conductance. We deem things more in terms of resistance. So we use components that have specific amount of resistance or variables amounts of resistance. These are called resistors, all right. We're going to do some breadboarding with these and understand these. All right, resistors are made of carbon, okay? And based on how they manipulate that carbon and how much is there, they can control how much current goes through it. Because the current, or the wire will go in one end and out the other, but the wire does not connect inside the resistor, all right? The only way for current to go through that, okay, is it has to fight its way through all the carbon that's in there. So we use resistors to control currents, and we give them a color code that we're going to get into. So the colors are on resistors for a specific reason. They tell us the size of the resistor. Okay? So when we see resistors like this, you might see a few in your TV. You might see a few on your motherboard. You're not going to see a ton like this. This is more for prototyping. You'll see some, I'll show you on some of the labs and some of the equipment as we look around, but a lot of the stuff now are all surface mount. Like your phone has a ton of resistors in it, but they're small, they're surface mount, so it's very, very hard to see those. Alright, so the symbol for a resistor is this guy. So when you see this, you need to know we're talking about resistance. We're controlling the amount of current that goes through that particular component. How do we know? Alright, so these are fixed resistors, okay? This means the values cannot change. So if I tell you that's a 10 kilo ohm resistor, that's a 10 kilo ohm resistance. There's a little bit of tolerance, so it might be a little bit more or a little bit less than 10 kilo ohms, but for the most part we classify it as 10 kilo ohms. Same with the one on the right. The one on the right can do the same exact thing. A little bit more different material. Alright, the resistive material, but that's a surface mount one. So that might be what one looks like on the inside of your phone or something along those lines. Okay? So they can look different ways, alright, but they all have the same kind of capability. So if we look at E, that's what you're going to see like inside your computer or something like that. It's an array of them. Okay, there might be radio ones, the metal film chip resistors in your phone or things like that. Okay, they just kind of have some different properties, different resistance properties. But these are generally what your fixed resistors are going to look like, which means we can't change the value of their resistance. They are what they are. Alright, so let's understand what the color code is here. And if I give this to you, you're going to have this on a test. The colors don't necessarily maybe look right on your screen here. That brown's not looking real brown to me. You can pull it up on your phone. There's an app for it as well. The resistance color code and what each one means. Alright, do I expect you to memorize these? No. Any question I have on a quiz or things like that, I will give you the color code. I expect you to understand how to use the color code, but I don't expect you to memorize the color code. Anyone who do the military stuff, I think they do ask you to kind of memorize that. It's on the ASVAB and things like that. Anyone wanting to go into electrical there. Alright, but what does it really mean? So I showed you a picture of a resistor before, and it had 4 bands on it. Alright, 3 colors that we use to designate the value of the resistor, and then the last band is either going to be gold, silver, or it may not be there. Alright, and that's the tolerance. Okay, with the tolerance, so let's say I give you a 10 ohm resistor, or let's make it easy. Alright, let's say I give you 100 ohm resistors, and the tolerance is 95, or is gold, which is 5%. So that means that resistor can be 95 up to 105. But we're going to call it a 100 ohm resistor. It's just kind of how the components and the carbon that they use and how exact it is. Alright, so it means that it's got a plus or minus 5%. So a 100 ohm resistor can vary anywhere from 95 to 105, and we're going to classify that as a 100 ohm resistor. That's always the last color band, is the tolerance piece. Alright, the first 3 bands we're going to have to pay attention to. So the first 2 bands tell us the first 2 digits of the resistor value. The third band tells us how many zeros there are going to be after the first 2 digits. It's really not that hard once you get it down, okay? So let's take a look at some of these here. So remember, don't ever read gold first. So in this case, we got like black, gray, and purple or pink or whatever you want to call that. What I think it's purple that's in the color code, and then gold. Colors are kind of hard to read here on the PowerPoint in that aspect. And I'll give you, when we do something like this in class, I'm going to give you some resistors. You guys need to find out the value. I would make sure that you have your phone out so that you can zoom in. These are tough to see the colors on this, and it really does help to use your phone. Alright, so let's do some example resistors here. And I do expect you to be able to do what we're doing now on a test, and on the quiz, and on the lecture quiz as well. Okay? So, that first resistor here, And I wrote the colors down so that if you don't have to decipher what the colors are on the screen if you got color blindness or things like that. All right, so that first resistor is green, brown, red, gold. So going through, green is a 5, brown is a 1. So I know that this is going to be a 5, 1. And then red tells me how many zeros to put after that 5, 1, 2. So 5, 1, 0, 0. And then it's gold, so it's going to be what? Plus or minus 5%. That's what's down there where the digit is for gold. Okay? So you can write that as 5100 ohms, or we like everything in engineering prefix or SI prefix, so 5.1 kilo ohms plus or minus 5%. Make sure I will count you wrong on a test if you do not put the tolerance plus or minus 5%. Okay, don't just tell me it's 5100 ohms because you're wrong. It's plus or minus 5%. So just make sure that you remember that for the quiz as well. All right, let's do the next resistor. Or why don't you pause the video and give it a shot here, and then I'm just going to go ahead and go through it. We have gray, red, yellow. So gray is 8, red is 2. So I have something that's 8, 2. So I write down 8, 2, and then yellow tells me how many zeros. There's 4 zeros. So I'm going to write 8, 2 and put 4 zeros after it, and then write ohms. And then it's silver, so I got to write plus or minus 10%. Okay, plus or minus 10%. And then I can take that number, that 8, 2, right, with the 4 zeros, and I can write that out as 820 kilo ohms if I want to. So instead of writing 820,000, okay, I can write 820 kilo ohms plus or minus 10%. All right, same with the next one. Why don't you give it a shot and then pause the video and then I'll work through it. All right, we got yellow, violet, black. So yellow is 4, violet is 7. We have something that's 4, 7. Black tells us how many zeros to put after it. 0. So we're just going to keep that yellow violet with 4, 7 and then plus or minus 10% because of the silver. So with black being the third color, we don't put any zeros behind that, so that's how we get all the resistor values that are less than 100. All right, so that one should be 47 ohms plus or minus 10%. All right, let's do the last one here. Go ahead and pause it, give it a shot on your own, and we'll come back together and go. Now, this is brown, black, gold, gold. All right, so now we got to think about a few things here, and it's tough to see on that screen. Probably. The multiplier for gold is 10 to the minus 1. The multiplier for silver is 10 to the minus 2. So gold's going to come into play here in the third color. But let's look. We got brown and black. So brown is 1, black is 0. So my first 2 digits are 1 and 0. And then gold, this is where it's a little bit different. It's technically a multiplier, so I can take 1 0 times 10 to the minus 1. So this is how, when we want to get resistors that are less than 10, okay, we're just going to move the decimal place 1. So this is a 1 ohm resistor. So instead of 10, that gold being the third color moves my decimal place 1 to the left because it's 10 to the minus 1. So this is a 1 ohm resistor plus or minus 5%. A little tricky on that one. But not a bad example for you guys to take a look at. Alright, other resistor surface mounts. Okay, you'll see like the number 123 on them. So we have the first digit and the second digit, very similar. It's just the last digit tells how many zeros. So this would be a 12,000 ohm resistor or a 12 kilo ohm resistor. So this is reading like a surface mount resistor. For physically in my lab, I'll pass around some surface mount resistors for you guys to take a look at. Alright, there's also alphanumeric labeling on some of these, 2 or 3 digits. One of the letters R, K, or M are used to identify the resistance value. Alright, the R, K, or M stand for this, okay, multipliers, and then zeros, okay. So you can treat it as a multiplier or a number of zeros. It really doesn't matter. Whatever is way simplest for you. So if we have this resistor that's a 22R, it's really 22 times 1. Okay? Then If the letter is in between two digits, it's a decimal point. All right, so let's look at the middle example here. We have a 2M2. So that's a 2.2 mega ohm. How do we know it's mega? The M, all right, the M is for mega, and that's 1 million. So that's why it's 2.2 mega ohms. If that was a K, it'd be 2.2 kilo ohms, okay? But it's an M, so it's 2.2 mega ohms. All right, and then the last one, we have 220K. So we have 3 digits there. So 220, and then K is the multiplier there. And it's times 1,000, so it's really 220,000. All right, that's really how you read these. You just need to know what R, M, and K are. The number of digits are going to be however many are in front, and then the letter tells you if it's a multiplier of 1, 1,000, or 1,000,000, and it also indicates where the decimal point is. All right, and we've been talking about fixed resistors. Now we're going to talk about variable resistors. All right, so variable resistors include what we call a potentiometer and a rheostat. Those are kind of their fancier names. Where a potentiometer we control voltage with, and a rheostat we use to control current with. So you might have one in your house if you control lights. So if you have a light dimmer, a little slide switch or a knob in your house, okay, as you move that up and down, it changes the current that's going to the lights in your house. All right, and as you raise or lower that current, your lights get bright or dim. So that's really where a variable resistor comes into. It helps you also change or tune in on your radio using a capacitor, resistor, and sometimes an inductor, an RLC circuit. That's how you actually fine tune to a specific radio station as well. So, or we're increasing the volume on your stereo. You're decreasing resistance, all right, to increase your volume. So think about those sort of things. Different things in your life where a variable resistor, okay, can come into contact. So this is what a potentiometer might look. We got a variable as we turn and rotate it. See the wiper arm there, how it connects to 1 and 2? That 1 and 2, the resistance changes as we go from 1 to 2. It might increase or decrease resistance. Okay, 3 is the neutral part, that's the completed path part. So we would have our hot that's coming in to like 1, 3, and then 2's going out to like our component or our element, all right? So as we move that wiper arm, we're going to change the resistor value so we can, make lights go down. We can change frequencies, right? So if we want a light that's moving really fast or make it move or flash slower, things like that. All right, so very, very, very important there. Now, you have to know the difference between these two symbols. This symbol on the left-hand side, we got a resistor symbol, and then with an arrow pointing in the middle. That's a potentiometer. A potentiometer is a specific type of variable resistor. So you do need to know that term, and you do need to know that symbol. All right, so that's a variable resistor, and a potentiometer is like a voltage divider. We're going to get into those later on when we start solving series circuits, okay? This is a voltage divider. All right, if we look at the next one over here, this symbol in the bottom right, that's also a variable resistor. So there's 2 variable resistors here. This one's called a rheostat, and this one controls current. Okay, so we want to control current. Here's what some of them might look like. Okay, and on the inside we can do the adjustment. There's a cutaway. So if we look at the first one on the left, there's only 3 showing here. There's one on top, middle, and then the right. And then the bottom is kind of like the cutaway portion if you want to see what's going on. So the first one we already talked about, the potentiometer. The middle one, okay, it's a variable resistor. We adjust the resistance with a screw. All right, so you can see on the inside cutaway, if we change that screw, there's an element that slides up and down there and changes the resistance. Same with the one on the far right. We're using a screw, but look, this time it's on a wheel, okay? The other one's kind of on a gear type drive or auger type system versus a wheel type system on here. All right, so if we take a look at, what it looks like on a circuit. Now, you don't need to write all these down, all right? We're going to get into these when we do series circuits and things like that, but here's what's really happening to a potentiometer. There's a total of 100 ohms across that resistor, but we can move the arm. So if we do a quarter turn, We're at a quarter of the resistance or 3/4 of the resistance. If we do a half turn, it's at 50-50. 3/4 turn, right, we're at a quarter and 75. That's really what's all that's going on there. So as we turn it, all right, we're changing the resistance value that we're using. All right, so the most common symbol for a variable resistor, though, is just a resistor symbol with an arrow and a line through it, kind of like the thermistor that's on here. But the thermistor is a variable resistor. So what does that work? Well, your thermostat in your house. So there's a resistor in there that is temperature sensitive. So its resistivity changes based on temperature. And that's how we control our thermostat in our house. We're going to get into that in another chapter in our series, parallel combo circuits chapter, when we do the Wheatstone bridge. Okay, we're going to get into depth about being able to control a thermostat, those sort of things. All right, photoconductive cell. Okay, what do those deduce, or what do those detect? Light. All right, so different values of light change the resistance on those. So if you have outdoor lighting at your house, right, that automatically comes on at dusk and turns off at dawn, you're using a photoconductive cell. Based on the amount of light that hits it, it knows, we're either going to turn the lights on or turn the lights off on that. Lastly, we have variable resistor here. It's a strain gauge. Okay, strain gauge doesn't sound normal to you, but we're measuring force. The most common thing you should think of is a scale in your house. You are straining resistance. So when you step on the scale, like a digital scale, when you step and put your weight on there, you're changing the resistor values. Those resistor values translate into a voltage. That voltage translates into your specific weight when you're standing on the scale. All right. Most simple circuit we can talk about here. We got a battery and a lamp and a wire, all right, and we're turning on a light. Now, most of the time we got to have enough resistance to protect the light to keep it from blowing, all right, but this is a basic drawing of a circuit. Do you ever use one like this in the real world? No, but this is for you to understand what's really going on here. Notice we're using the current path, not conventional path. We're saying that electrons are flowing from negative to positive and they're going through the light bulb. Okay, no switch on this, just a basic simple circuit. This is what it's going to look like to you more in the real world. All right, we got a DC source here on the left, right, that plus or minus voltage, and we have a lamp or a light or an LED in this scenario. So this is how we would draw it in a more of a schematic type view, all right, rather than a conceptual working view. But I want you to start thinking about this, all right? I like this little comic here because it kind of really defines it, and we're going to get into it when we use Ohm's law. So, but remember, what was voltage? Voltage is the force we need to push electrons. And what's pushing electrons? We're creating current to flow and getting amperage. All right, so voltage is pushing current through, where resistance, the guy standing on top of the rope, okay, that's ohms. He's limiting how much current can flow. So all three of those have a relationship that we're going to learn about soon. We talked a little bit about it in digital electronics, those of you that took that, all right, but Ohm's law and how those three work together for pretty much every single type of electrical device that we use in the world. All right, we're going to get into a lot of components here. I'm going to expect you to know every single symbol and what type of switch or what type of component it is tied to. So we're going to talk about switches first. All right, so a little bit different here. The throw refers to how many circuits are affected by the movable arm. All right, and the pole is the number of contacts that are available to form a circuit. So double pole, double throw is what we're going to kind of think about as we start talking about these. Single pole, single throw. Okay, so think of like the throw as the switch, so like a switch in your house, all right, like to turn on your lights or things like that, or just a basic, switch that we're going to use and talk about. So let's go through these. I do expect you to know all these symbols. All right, so I've given you the symbol and I've given you kind of the nomenclature on here and a picture of what it physically looks like. So we have an on-off switch. This is known as an SPST, a single pole, single throw. All right, so if we look at the symbol, single pole, single throw. Throw is the little arm piece that goes up and down, so it has one of those. and it only connects one circuit. We're completing the path for one circuit there. That's why it's a single pole, single throw. Alright, the next we have is an SPST momentary, or a push to make, or a push button switch. And in this case, since we call it push to make, this is actually a normally open push button, which means if we don't do anything to it, there's no electricity. So it's an open circuit until we push it, alright, and then it closes and the circuit works. Okay? So think of like a vending machine, right? It's just sitting there, normally open, and then you go order a Mountain Dew and you press the button for Mountain Dew, or you type in the right code and the switch closes and the Mountain Dew drops out for you. Alright, the next one is a push to break. It's still an SPST, okay, but it's a normally closed push button. Okay? A great example of a normally closed push button for us is an emergency stop, right? We need that circuit connected all the time, but then when we hit the button, we need the circuit to open for safety purposes. So that's where we have an SPST. So both of those are SPST, single pole, single throw, okay? Because there's only one element, so the throw, one element that opens or closes the circuit, and only one circuit is being affected. But we have push to break, push to make. Both of those are push buttons on those bottom two. All right, make sure you know all these symbols and the tags associated with them. They will be on your lecture quiz, they will be on your big quiz, and they will be in your homework. All right, another one. So you're asking, well, what if we have two circuits attached? All right, so that's where we have our SPDT, our single pole double throw. Notice what's the difference there, okay? We have the one pole here that's a little bit different in the book. So there's the one arm, and it connects two different circuits, A and circuit B. So that's why it's an SPDT, single pole double throw. So remember, the pole's the switch piece, and the throw's how many different circuits it's kind of connected. You can go back and forth in industry and kind of argue which is the pole, which is the throw, or things like that. But all right, we have a single pole double throw switch, the second one here, that has A, and B. All right, so what that is it has two different ons and one off in the middle. Okay, so we can take a look at these different switches here. So if there's a switch, and it sits in the on, off, or on position, or the off, and then a different on, so it can control two different circuits. So that's what we're going to do. Make sure you know the symbols, okay, and time correct. This is a double pole, double throw. All right, so there's two circuits that are being, on this one, there's two circuits being closed at the same time. All right, and two actual latches closing at the same time too. Alright, so this is a double pole, single throw. Those two latches are connected at once though, so don't get super confused here. Look at the second one. There's a double pole, double throw. Alright, so now there's two latches, but it can control two circuits. Where on the first one, there's two latches that control one circuit. So double pole, pole's the arm in the middle, and then the throw, how many circuits? So the first one, the double pole, single throw, the top one, okay? There's two poles, that's like the light switch at your house, right? And they can control one circuit at a time, all right? And then on the double pole, double throw, the bottom one, okay, there's two poles, right? But they can control two separate circuits. We sometimes use that as a knife switch as well. And we're gonna work through those on the lab. It'll help clear up some of those. But make sure you know all the symbols and the correct DPDT or DPST or those sort of things, all right? Multi-way switch or rotary switch, or looks kind of similar to that variable resistor we talked about, but it's a switch that we have an off position, and then we can rotate through different positions. The best one I can think of for you guys here is, think about like a fan at your house, and you have three different speeds. You have off, then you have level 1, 2, or 3, or high, medium, and low on the speed of your fan. So that's really what you're doing there, is you're turning it to give it potentially more voltage or something, or being able to change the speed. So this is a multi-way switch, okay, or a rotary switch, if we want to get with all the different terminology. All right, so what do we use switches for, right? We open and close circuits. That's really what we're doing. So at your house, you go turn on the switch, turn on and off the lights, those sort of things. If the switch is open, the lights aren't on. If the switch is closed, the lights are on. Very simple, very basic, all right, but that's what we use switches for, turning things on or off, essentially. All right, we can use like a single pole double throw to control two different lights. So what I want you to think of is in your house, say you walk into one side of your living room or something and turn the light on, and you can walk out the other side of your living room and turn the light off. That's what a single pole double throw switch is doing. All right, so you can do those sort of things. And they're wired a little bit differently, but I want you to think about, kind of like that when we're going through the lamp scenario that you see here. All right, so we're going to take it what we call mechanical limit switches, and we'll get in depth on the 870 trainer with this one, particularly station 2, where we can actually physically see the limit switches. It is exactly what the verbiage means. All right, when the carriage tray in station 2 gets to a specific point, it hits that lever closes, all right, and lets us know it's there. So they come in all shapes and sizes, multiple different uses, all right, but we're going to really pay attention to the arm. That's the long silver piece that's kind of sticking out, or the mini one is just a little push button that kind of sits on top. And we'll go over it a little bit more in class, all right, but we really need to make sure that what's the point of a limit switch? We want to be able to detect that something is present. We're going to detect if an object is there or not. And we're doing that by mechanically closing a contact. And when that contact closes, we make an electrical connection. Alright, so it's going to look like this. So the upper left-hand corner, okay, that little arm with a flag looking thing on it, that's the symbol for a limit switch, also on your test, okay? But this is what they look like on the inside, okay? So on the very top, that black looking armed thing, that's the mechanical lever. When that gets pressed, it pushes the screw-like thing down and closes the contactors 1 and 4. When that mechanical movement presses down and closes the contactor, we are completing the flow of electricity. We're making an electrical connection then using a mechanical movement. Alright, so that's what a limit switch does. We're taking a mechanical movement, pushing a button per se, pressing down, and making it make an electrical connection. Alright, so here's what it looks like on a PLC symbology, and we'll get to that more in the PLC class, but you've got some inputs, outputs, and how it turns on. Alright, so it might, for our sake, on station 2, when the carriage gets to one end, right, and closes the contactor and all the other steps complete, it'll know to turn on the motor to return the carriage back home as long as it's there. And when I'm talking about station 2, we're going to get into this in more depth, right? But if we're looking straight down on station 2, we got 2 limit switches here, 4S1 and 4S2. It's good to know those, all right? 4S1 lets us know the carriage is at home, okay? We have to write a program to know if the carriage is here, do these steps. Limit switch 4S2 means that the carriage is moved across. Well, we have other steps that we have to do once the carriage is moved across, but we need to know that the carriage is physically moved across to do those steps. So it's kind of procedural and methodical as you go through those. Alright, so station 2, what are we doing? Okay, we're checking for a port valve and we're making sure that the valve body is high enough, okay, using the ultrasonic sensor. So we're looking down to make sure that the height of the valve body is correct. But it can't do that if we're not in the process of moving or knowing where we are in relevance to 4S1 and 4S2. Alright, so we'll cover that a lot more in depth when we do our get on hands-on with the trainer, okay? But those are the limit switches we're talking about, and we'll physically take a look down on them as well. Alright, this is a vendor page. So if you have to go find a replacement switch, all right, you can look at the different ratings, the different voltages, what it can handle, what's going to do the switching, all right, all those different things. So you're going to look up this if you have to order replacement parts. So this might be something you look up online, like a data sheet that you know about this particular component. All right. This one we'll come back again to in the PLC class, but notice that we can't start or do anything unless we're at the home position, which is 4S1. And the PLC tells the trainer, all right, all the different components on there, well, if we hit the start button and we're home, then we're going to do everything in step 1 right there. And we're going to take the measurement, the part reading, and things like that. And then when we get to 4S2, all right, Then we're going to have to extend the lift cylinder and decide if we are going to accept or reject the part and send the carriage home. So there's where it's going to play an integral part of our PLC programming and our thought process as we go through and write our ladder logic for that. But that we're going to get to when we get to the 1340 class, all right? But I just want you to see this because you're going to have to know this when we troubleshoot in here. So you're not going to, not see this for a few years, but we are going to use this in the troubleshooting process, but you need to understand what some of these symbols mean and how to go through them. All right, so with limit switches, what can go wrong? Well, it's mechanical. So anything can break. The arm can break, the internal contact can break, the welding contacts can break, all right? It can become arc and pitted, and over time, bad loose. The most common one for us on the 870 trainer is it gets bent, all right? And it doesn't make contact. It's not broken yet, it just gets worn, all right? So for us, that's kind of an incorrect adjustment, and we gotta check that occasionally, okay? So what are some symptoms that the limit switch is out, right? No change in signal, no signal, continual signal. For us, maybe the motor doesn't stop or the clutch doesn't kick in, or the clutch does kick in, the motor won't stop because the signal wasn't reached that the carriage actually moved to the position that it's in, all right? How to adjust and check. So we can check for continuity, so we can push open and close physically the arm, all right, and use a multimeter to check and see if we're getting continuity as we open and close it. We can also physically inspect to make sure that everything's good. We can check voltages. Okay, we're going to go through all this when we do some different troubleshooting on the 870 trainer so that you figure some of these things out. All right, next, moving on, fuses, circuit breakers, all right, and why we use these. We use these to protect electrical equipment. So inside your car, you have fuses. Now they're going to look like kind of the one towards the middle with the two prongs and clear glass. That's how they're going to look in your vehicle. But when we protect electrical equipment, we use the cartridge fuses on the left-hand side. All right. Sometimes you can see in them, sometimes you can't. All right. But they're used to protect equipment. So the symbol for a fuse is shown down below with D. And what happens is there's literally, it's just a wire. Okay. And that wire, when it receives too much current, that wire breaks. All right, it blows right open. So when you say you've got a blown fuse, literally that's what happens. It got too much current and blew. But your equipment is protected. All you have to do is replace the fuse. So instead of replacing large circuit breakers because something keeps blowing and that's expensive, we can put a fuse in front of it and we can replace fuse. Fuses are cheap, all right, when we get like a surge or something like that. So that's one way of protecting it. The other way we can protect is using a circuit breaker. So make sure you see the circuit breaker symbol and know that. Circuit breakers like in your house, okay? You walk over to the power panel and there's a bunch of switches in there. That's a circuit breaker. So if you have a 15 amp breaker, if you plug in your vacuum or something and it draws more than 15 amps, it trips the breaker and that power shuts off, all right? So that's to keep the entire power from going off in your house. Just everything on that one circuit might go out in your house, okay? So make sure we know the symbol for a fuse, what a fuse looks like. Make sure you know the symbol for a circuit breaker, what a circuit breaker looks like. All right, next, this is important if you're doing electrical engineering and you're designing buildings. You need to size the right wire for motors, lights, and there's a difference between control cables, so whether you're doing PLC stuff or whether you're going to motors and running three-phase 480 volts. It's very important for us to understand how to size wire, all right, where it comes from. So when we talk about wire gauge, we talk about AWG or in circular mills, okay? Either or, we're talking the diameter or what we call the cross-sectional area of the wire itself, all right? Some can get pretty small. If you ever cut open like a USB drive, those wires are insanely small, very, very hard to fix, okay? But it's a little backwards with wiring. The larger the number, the smaller the wire size. The larger the number, the smaller the wire size. So a 40 gauge wire, okay, 40 gauge wire is very small compared to an 18 gauge wire. Now what's in your house? Your house is 14 gauge, so you have a 2 conductor 14. So you have a hot, a neutral, and ground. And we talked about that in the last lecture when we looked at the different plugs and those sort of things. So, we have to gauge wire based on different elements. You know, what are we running to? How much current is the motor going to draw? All right, so if you have a hot tub at your house, you can't use a 2-conductor 14 wire. You have to drop to, or not drop, but you have to raise to a number 10 size wire. You need a larger wire to run 30 amps. All right, you might have to run to like a size 8 wire to run 60 amps. So the more amperage, okay, the larger size wire you're going to need for multiple reasons. Okay, because if you use too small of a wire, it's going to burn up and melt and cause a fire. That's really essentially it's for safety. All right, can you use a really small wire to draw big voltage? Oh, absolutely, for maybe a couple seconds until it blows up. All right, that small wire just becomes like a fuse to that large voltage. All right, and it'll just blow right up. All right, so for this, you need to understand how to use this chart. This is on your tests, okay, and it is going to be on your quizzes, and all of that will be on your midterm and your final. So make sure you know it. But I'm going to teach you the easy way to understand this chart. Okay, on the far left-hand side, that's the wire size. Okay, the AWG. So wire size 1 to 25. Okay, I'm not going to ask you questions about its diameter in inches or millimeters. I'm not going to ask you for even the cross-sectional area, but I do want you to be able to calculate the resistance per 1,000 feet. All right, we are going to do it in feet. We're not going to do in kilometers. It would be the same thing. Okay, so we're going to work through a couple examples. I don't expect you to memorize this, but on a test I will give you this chart and expect you to be able to use this chart. Okay, this chart is in the National Electrical Code book, so when you build, all right, and electricians have to come in, or you're the engineer that gives stuff to the electricians, you have to make sure that all the wires size correctly. So let's do an example. So I've taken that big chart and cut a chunk down. So we're going to look specifically at 14 gauge wire. So 14 gauge wire, okay, if I look kind of in the middle there, it has 2.52 ohms of resistance per 1,000 feet. Okay, it has 2.52 ohms of resistance per 1,000 feet. So hopefully pause the video and find that number if you can't do it right now. So let's take a look at the example. It says, what's the resistance of 400 feet of wire that's 14 gauge? So what's the resistance of 400 feet of 14 gauge copper wire? Well, I've given you the exact one, 14 gauge here. So we're just going to base it on 1,000 feet. This is very, very simple to do. Okay, so we're going to take 400 divided by 1,000 and multiply it by the, not by 14, okay, we're going to multiply by how many ohms of resistance that specific size wire has per 1,000 feet. All right, so when I write that out, I'm going to write 400 over 1,000. That's the ratio of how much wire I have. And then I know it's 2.52 per 1,000 feet. So 400 divided by 1,000 and then multiplied by 2.52. Make sure you're getting the correct answer that I do when you do this. But where does, okay, so the 400 comes from here. That's the amount of wire that we physically went to Home Depot or Lowe's and had to buy. Okay, the 1,000 is coming from the chart. Okay, because it's 2.52 ohms of resistance per 1,000 feet. Okay, and then I'm using 14 gauge wire. And then the 2.52, that comes from the chart as well. The 2.52 is there. It's 2.52 ohms of resistance per 1,000 feet. So when you do the calculation, you should roughly get it's about 1 ohm of resistance. Okay, this is really big in transmission lines, long electrical lines that go like 100 miles before they have to reach a substation, because when you're doing thousands of feet of wire, there's going to be a large amount of resistance over certain distances. Okay, so that's really what you're going to kind of pay attention to. So I mean, this, if we look from 1,000 feet, a mile is 5,280 feet. Roughly, if we take 2.52 times 5, you're going almost at 12 ohms of resistance every mile. All right, 100 miles, okay, that's going to add up quickly, 1,200 ohms. So what's going to happen when we have that resistance? You won't get as much current and your electricity won't be as efficient. All right, let's do one more example here. Why don't you give this one a shot on your own? So pause the video and see if you can calculate this. This is for what's the resistance of 1,500 feet of 8 gauge copper wire. You will have to do this on the test. Okay, same concept. Okay, we're going to take 1,500 divided by 1,000. That 1,000 will never change because it's based on the chart. Okay, so the 1500, that's how many feet of wire you and I went to Lowe's or Home Depot and bought. Okay, 8 gauge wire. Okay, we know what the resistance is per 1,000 feet. The 1,000 still comes from the chart here, and it's 0.6281 per 1,000. So when I calculate this, you're going to get 0.94215 ohms of resistance. Okay, so that's going farther than 1,000 feet. We're not going to have very much resistance, so that's good. And this is why you have a higher gauge wire. So when you buy an extension cord or something for your saw at your house, that's why you want a better extension cord. You don't want the little scrawny things. You're going to blow it up because you're going to want to run at full amps. All right, you want to run 12 amps on your saw so you can cut through your wood. You don't want it dying down because you can only pull 5 amps through that scrawny little wire. All right, so always protect yourself. Have a big, heavier duty extension cord, and that's why it gets more expensive, because the wire size changes. Don't always go for the little cheapo. It does make a difference whether you're using like an 8 or a 10 size wire versus a 14 size wire. Okay. Alright, let's talk about the 3 different kinds of ground we're going to talk about here. You need to know these symbols. We got A, B, and C here. These all mean ground. Okay, they're just for different purposes. Okay, so A, that's over voltage protection. That's the most common one we use. Alright, that's one that's going to protect you from lightning. So outside your house where your power panel is, there's about a 6-foot rod that goes into the ground that's tied to your panel. So if lightning hits, you give it a path to go to. Okay. 2, voltage stabilization. It's a common reference. So like say you're taking readings on your vehicle and you touch your one side of your meter to your chassis. Just a common reference ground. Okay. And the other one is safety. What if neutral breaks? So we're going to use that kind of ground. That's more to protect large equipment or something. If neutral snaps, that current has to have somewhere to go so you don't fry things. Okay. And you're going to be able to ground it. Okay, so ground for safety. The most common one we're going to use, though, for everything I draw is going to be A. Okay, when we draw our circuits up. Basic circuit with ground connectors. Now, we don't always draw it this way. This is kind of how the author does. I don't ever draw it with 2 grounds. I just complete the path and put like 1 ground over on the left. All right, but simple circuit with ground connectors. That's what it's going to look like. Okay, so an electric circuit. Okay, it consists of what? A voltage, a path, and a load. So let's take a look at this previous path. We have a voltage, 12 volts. We have a path, so it's got to go through 12 volts back to ground. Okay, and the load is the lamp. All right, so any equipment that's using voltage and current, that's what we call the load. So the 3 basic parts of a circuit: a voltage, path, and a load. Okay, so flashlight, voltage, path, load. Metal strips, the path. Okay, voltage, and then the load is the lamp. Okay, we just have the switch that turns it on and off. Okay, and if we were to draw that up, it would look just like this as a schematic. This is a schematic of a flashlight. Okay, you got your battery, you got your switch, you got your lamp. Okay, pretty basic. Now, how do we take some readings? Okay, you've heard me mention it. This is a digital multimeter. Okay, why is it a multimeter? Well, we can read AC voltage, DC voltage, current, resistance, continuity, all right, and a few things like that. And there's different settings for this, and we can do AC and DC current, AC and DC voltage, all right, resistance, continuity helps, that tells us if a wire is broken. All right, we're going to go through this in class and learn how to use this stuff in our labs a little bit better, because it is important where you put the plugs in there. Notice there's 2 yellows, 1 red, and 1 black. Those all mean something. We're going to go through it. But we're going to learn how to use a digital multimeter in class to take readings and troubleshoot on the 870 trainer. Now, you can't see really well in the picture here, but there's a V with a tilde above it. Anytime we have a tilde, that means it's AC, so our AC voltages are on the left-hand side. Our DC voltages have a straight or dashed line across the top. That's how we know that we're reading DC voltage. So when we do everything on the trainer, we're going to be using DC volts. Okay. Then over here we have continuity or ohms. It's not necessarily pointing to the right spot, but just below where that arrow is pointing, those are all the different readings for ohms we can read up to. It's technically pointing to continuity right now, I'll cover what that is and how we use that to troubleshoot in class, but that lets us know there's a complete path for our circuit. And we have amperes over here. And once again, the line on this one is pointing to the DC amps because it has a straight line or a dashed line above it. The one with the tilde is the AC current. Okay, the second line there that's popped up and that it's pointing to. That's our AC current. Okay, this is an old school meter, uses Darcinal movement. It's an analog meter. We are not going to use any one of these, all right, but it's a volt-ohm meter. You just got to be able to read the needle movement, all right, and how you understand those. So for one of these, no resistance means infinite ohms. Okay. Now, how do we measure current in a circuit? And we're going to do this in a lab, but I want you to understand a couple things. The most important thing, when we measure current in a circuit, the meter has to be in series with the components. It means we are physically going to put the meter in the circuit using the probes and the connections to the meter. All right, the meter has to become part of the circuit, just like a resistor, just like a light, everything else. So when we measure current, okay, it's a series circuit when we use the multimeter. That's important. To measure current, the meter must be in series. Okay, that's on your test. Okay, that's in your labs. That's on your lecture quiz, everything. To measure current, the meter has to be in series with the circuit. To measure voltage or a voltage drop, okay, in a circuit, and it's shown on the schematic here as well as the diagram, okay, the meter has to be in parallel and the circuit has to be on. So we measure voltage with a meter in parallel. Measure voltage with the meter attached in parallel to the component. So you can see the two probes from the meter that's reading 9 volts across that resistor is touching each side of the resistor, and the resistor is connected. All right, so to measure current, we have to be in series. To measure voltage, we have to be in parallel. And to measure resistance, we have to disconnect the component from the circuit and then read across it. So we're measuring resistance, we're disconnecting the component and reading across. So once again, to measure current, the meter has to be in series. To measure voltage, the meter has to be in parallel. To measure resistance, we have to disconnect the resistor or the component from the circuit so it's not live and take a resistive reading across it. Okay, there's just a picture of what's going on. Okay, reading current, that's the circle with the A. Alright, so it has to be in series with the circuit. The circle with the V means we're reading the voltage drop across that resistor. Alright, and then if we wanted to read resistance, that pink box means we're taking the resistor out and reading the resistivity of the element. We're going to do labs in class and hands-on so that you guys get like a feel for this, so that you really understand what's going on with that. And you're going to have to know how to use the multimeter and that sort of thing. Alright, so here's what we're going to do. This is the end of the lecture. I'm sure you guys are stoked about that. But just for review, all of these are going to be on your test. Alright, so what I'd like you to do is, and they'll be on your lecture quiz, is write them all down, pause the video, and see how many of these you can answer on your own right now just after going through the lecture. I'm going to post all the answers here in a second. Alright, but go ahead and pause it, draw them all down, and then just fill in the ones that you think you know or the ones that you got right. Okay, and then fill in the others, and then you're going to have to study. Okay, so I'm going to go through these real quick. So we got a battery or a DC voltage is fine, a resistor. Okay, this is a specific type of variable resistor. This is a potentiometer, so that one I'm specific on. This one's a rheostat, okay, a variable resistor. So those are the two symbols. This one's a lamp. We should know that these are ground. Okay. This one is a normally open push button. The next one's a normally closed push button. This is a single pull, single throw switch. This is a single pull, double throw switch. This is a double pull, single throw switch. The dashed line here means that we're kind of combining these two together. So it's a double pull, double throw switch. Okay, we should know that this one's a rotary switch. And then we should know this is a fuse. This is a circuit breaker. This is a voltmeter. This is an ammeter. And this is an ohm meter. So those are the last three that we just did, learning how to use the multimeter when we do this. Okay, so you should hopefully know all those symbols along with any of the other ones I talked about. on this, you need to make sure that you know all the key terms. They are at the end of the chapter in your book as well, but these will all be on the test. I do expect you to know all of the key terms as well. Remember, you can always pause the video and back it up and do that sort of thing. Alright? Any questions, come to class with them, and when we talk about labs and that, you're more than welcome to answer, or feel free to email me. And if you need to do an online meeting or something with me, we can do that as well.